All right, let's start with these homework problems that I assigned you guys, and hopefully you guys didn't have too much problem with this. So, number one, it says here, a jet plane traveling at 1,800 kilometers per hour, okay, that's 500 meters per second, pulls out of a dive by moving in an arc with radius of 6 kilometers, right? So, if you were to look at an airplane, like let's going for a dive like this, and then in order to pull out of this dive, they have to go make a nice big arc, right? A circular arc like this. So here, this is the radius. This radius right here is rather large, right? Look at that. So radius is actually 6,000 meters. You have to keep these in meters, seconds, right? And V, the speed, this is V basically, in meters per second, right? So V is equal to 500 meters per second. So those are what's given to us, right? And then the question is, what is the plane's acceleration in G's? I think we had problems similar to this, right? So we know acceleration, since this is going in a circular motion, the centripetal acceleration is equal to, right, v squared over r. So that's easy, okay? So if we were to actually plug in these values, where v is 500, and you have to square that, divide that by 6,000, right, meters, what we get is 41.7 meters per second squared. So that is the acceleration this pilot would be feeling, right? Including, right, acceleration due to gravity that's not really calculated in there, okay? So what's going on? How many G's will this pilot feel, okay? So that same acceleration, which is 41.7 meters per second squared, can be converted into G's. So 1 Earth G, right, is equal to 9.8 meters per second squared. So notice how the meters per second squared gets canceled out and we get G's. And that is equal to 4.25 G's. So what is the significance of this? That 4.25 G's represents 4.25 times the weight of the pilot. So you would, if you were the pilot, you would weigh 4.25 times heavier. That's why when you see those movies, like, in the fighter jet plane, like making a bank turns, right? And there's pilots are like, they're breathing really hard because imagine 4.25 of you laying on top of you. You'll have really hard time breathing, right? That's why they struggle when they come out of a nice turn, and this turn is actually 6 kilometers, and that's pretty wide turn too. But they'll feel that many G's. Okay. All right. Let's take a look at number 2. Calculate the centripetal acceleration of the Earth in its orbit around the Sun and the net force exerted on the Earth. Okay. We're not going to worry too much about the net force yet, okay, because we haven't covered about the forces. But let's think about just finding the centripetal acceleration of Earth. Now we know Earth is going around the Sun, so there has to be some kind of centripetal acceleration, right? So let's draw a little diagram. So here's my sun, right? Sun, Mr. Golden Sun, please shine down on me. Mr. Sun, Mr. Golden Sun, hiding behind that tree. There you go. That's my sun, right? And Earth, here's Earth, right? And this Earth is going to go around the sun, and because it is going in a quasi-circular orbit, you could treat it as circular motion, okay? Now, first of all, we have to know a few things. What is the radius between the center of the sun to center of the Earth, right? Well, they give us that right here, the orbital radius, right? So that is equal to my r, right? So the radius between the sun and the Earth is equal to 1.50 times 10 to the 11th meters. That's pretty far out, okay? But that's not the only thing, right? Because we have to find the speed of our Earth going around the sun, because now we know the radius, right? And since a sub c is equal to v squared over r, we got to find what the v is, because we know the r, right? Well, we know v, the speed of the Earth, is equal to, right, the distance that Earth travels around the sun, which is 2 pi r, which is a circumference, right, divided by the period t. Okay. Well, I think we calculated this t before, okay? This period, which is 365.25 days, right? And then we converted that into seconds by saying there are 24 hours per one day, right? And then there are 3,600 seconds in 1 hour, right? So all these can cancel out nicely, leaving me with seconds, right? So I think when we worked it out, we got something like 31 million, right? 557,600 seconds for Earth to go around the sun, right? So now we have all the ingredients to figure out what the speed of the Earth is. So let's plug these values in. So 2 pi times r, which is 1.50 times 10 to the 11th, right, meters. Divide that by the period, which is 31,557,600 seconds, right? And what do we get? Well, this doesn't look that big, right? I think it's about 29,865.32 meters per second. Well, that's pretty fast, actually, right? That's pretty fast. Well, how fast is that? That's approximately like 66,800 miles per hour, right? Just to give you an idea how fast that is. That's approximately 66,779.6 miles per hour, right? So that's relatively fast, right? Well, let's now plug this here and this here to see how much acceleration the Earth should feel as it goes around the sun, right? So here, now we have all the ingredients. So we place 29,000, right? 29,000, 865.32, right, meters per second, squared. Divide that by 1.50 times 10 to the 11th meters, right? So even though when you square this, it's going to get a huge number, but this distance is huge. This has got 11 magnitude, right? Magnitude of 11 orders. So if you use your calculators correctly, right, what do we get? Well, it's pretty small. It's 0.0059 meters per second squared. So we hardly feel any acceleration at all, actually. Right? On Earth, we feel 9.8, right? But this is just negligible. Okay? So we don't even have to worry about. Now, if you want to find the net force of the Earth, what you need to do is multiply that by the mass of the Earth in kilograms. And mass of the Earth is pretty huge, actually, right? It's like 6 times 10 to the 24th kilograms. So it's huge amount of attractive force. But we'll talk about that more in detail next time. Okay? But this is good enough. So compared to a jet pulling out of a dive, giving you 41.7 meters per second squared, Earth really doesn't feel that much centripetal acceleration at all. All right? Next. All right. Will the acceleration of a car be the same when it travels around a sharp curve at 60 kilometers per hour as when it travels around a gentle curve at same speed? Well, if you think about it, I mean, you could just do this analytically, right? You could think of sharp curve. Let's give sharp curve radius, right? So sharp curve is radius here, right? So radius, let's say, is 50 meters. So the car comes in, and then just goes around a sharp curve with a radius of 50 meters. And let's say the other gentle curve is a lot bigger turn like this, and the radius of that, right? Let's make that like 100 meters. So it's got much bigger turn, right? So this is sharp, and this will be gentle. Okay? Now, we know acceleration is equal to, right, v squared over r for circular motion. So for the sharp, well, we should convert this into meters per second. So let's do that. So here, v is equal to 60 kilometers per hour. So if we convert that, in 1 kilometer, there are 1,000 meters, and in 1 hour, there are, 3,600 seconds, right? So if you work that out with your calculator, I think you'll get something like 16.7 meters per second, okay? So if you plug in this v at 16.7 meters per second, you get 16.7 squared, divide that by radius of only 50. Right? So this should give you your acceleration to be somewhere around 5.56 meters per second squared. However, for the gentle curve, your a sub c is equal to, right, v squared over r, and the speed stays the same, so this is still going to be 16.7 squared. Divide that by 100 meters is the radius. Therefore, this comes out to 2.78 meters per second squared. So the answer is no. You will not have same, right, acceleration. So no, right? The car will not have the same acceleration. right? The one with bigger radius will have less acceleration than the smaller radius because you're dividing it by a bigger number, so you should get a smaller value. All right. Any questions? All right, so now let's take a look at some multiple choice questions on the next page. All right, so here, a race car is traveling at a constant speed, right, around a circular track. What happens to centripetal acceleration of the car if the speed is doubled? Well, A sub c is equal to v squared over r. Right? Well, if we double the speed, our new A sub c, I'm going to just say A sub c prime, or blue A sub c, right, is equal to, when we double the speed, we get 2v, right, squared over same r, right, same r. I guess I could leave the r's. Well, our new centripetal acceleration will now be, right, if I square what's inside the parenthesis, it becomes 4v squared over r. Well, isn't this exactly same as A sub c original, right? Therefore, my A sub c prime is 4 times the original A sub c. Therefore, the correct answer would be C. All right. Next, questions 2 through 5 pertains to the situation described below. A 1,500 kilogram car travels at a constant speed of 22 meters per second, so we know that this is v, around a circular track that has a radius of 80 meters, so this is r. Right, so we have v is equal to 22 meters per second. R is equal to 80 meters. All right, now that we know that, let's take a look. Which statement is true concerning this car? A, velocity of the car is changing. That's it. Why is this statement true? Because even though it's going at a constant speed, velocity is changing because the direction is changing. Other ones, I mean, I don't think we even have to read it, but let's go through it. The car is characterized by constant velocity? No, because direction is changing, so the velocity is changing, so it's not constant velocity. So that statement is false. The car is characterized by constant acceleration? No. The acceleration magnitude may be same, may be constant, but the direction of the acceleration is always changing because it's always pointing towards the center no matter where the car is. So since the direction is changing, acceleration is not constant. Okay? Don't forget, vectors have magnitude and direction. Okay? What about D? The car has velocity vector that's pointing along the radius of the circle. That is also wrong because velocity vector is always pointing tangential to the circle, not radial. And E, the car has acceleration vector that is tangent to the circle. No, 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 right? Acceleration vector will always point towards the center of the circle. Therefore, that's why it's called centripetal acceleration, center seeking, right? So that is also wrong. So the correct answer is A. All right. Number 3. What is the magnitude of the acceleration of the car? Well, we could figure that out, right? The magnitude of the acceleration, a sub c, is equal to just v squared over r. Okay, so if we substitute all that variables in there with 22 squared over 80, and if you work it out with a calculator, I think you get something like 6.05 meters per second squared, and 6.05 rounds to 6.1, so that looks like A. Right? All right, and number 4. What is the average velocity of the car during one revolution? Right? Well, average velocity, by definition, is change in position over change in time. Remember from chapter 2? Well, what's the change in position when it makes one complete circle? Change in position is 0 because it starts at one point and it's going to come back to the same starting point. Therefore, my change in position is 0 divided by change in time. So it doesn't matter what time it is, it's still going to be 0. So 0 is the correct answer. Popular wrong answer would be 22. Number 5, determine the magnitude of the net force acting on the car. Well, we know the net force is equal to ma. And since there's only one acceleration, which is mac, right, we already know what that is. So the mass, which is 1,500 kilograms times 6.05, right? And we'll get our answer to be, I guess, something like 9,075, right, newtons. That's similar to, right, 9.1 times 10 to the 3 newtons. So that will be C. All right. And this, we should know. I think we went over this in your notes. If we have something going in a circle and then it's released at this point, will this object go this way, this way, this way, or this way? And we should already know the answer. And that is this way, right? So B is the correct answer. All right. Any questions? Excellent. All right, so let's move on to today's notes. Now, this is, again, something that we already did previously, but we're going to revisit this. So up to here, we already did this, so we already know what to do, right? So this page itself is just a repeat, because we know the speed is equal to distance divided by time, and 2 pi r over the period t is how we find the speed, right? But we're going to actually try to substitute this into the first equation, right? Equation 1, which is v squared over r is equal to a sub c. So if we substitute this into here, what do we get? My a sub c then becomes, right? Ready? Here we go. 2 pi r over the period t, quantity squared, divided by r. So here I get, if I square the top here, I get 4 pi squared r squared, and then if I square the bottom, I get t. Now r right here, divide by r, right? Divide by r, and that is same as 4 pi squared r squared over t times 1 over r, the reciprocal, right? Notice what happens to one of the squares of r and r at the bottom. So this, I forgot the square, the period, sorry, right? So here, one of the r's would cancel out. So my a sub c now can also be represented as 4 pi squared r divided by the period squared. So that means, even though when I see this, people may think, well, acceleration, centripetal acceleration should be inversely proportional to the radius. That is false, actually, because this velocity itself has radius built in. And if you plug in the velocity with this equation, this radius is now directly proportional to my a sub c, right? Or should I say a sub c is directly proportional to my radius. So as my radius increases, right, my acceleration, centripetal, should also increase, assuming my period of the circular motion stays the same. Okay? So please understand that. So a sub c is directly proportional to, right? Or should I say, the fishy thing, right? Directly proportional to the radius, not inversely proportional to, because of this rule. Okay? And that's all it really is for this one. Okay? And that's basically what we just did. Okay? So a sub c is directly proportional to r. And this will come handy later when we talk about Kepler's law. And it is also inversely proportional to the period squared. Okay? So Kepler utilized this actually to get the planetary motion and his Kepler's laws. Okay? So that was a pretty fast 2 pages. Now comes the real stuff, right? So here, if we were to think about what we had previously in chapter 2, we had linear acceleration. When things were going linearly, in linear motion, right, we had a linear acceleration. And linear acceleration, also known as atangential, right? So linear acceleration, right, is a tangential, right? A tangential. And a tangential, we already know this already, and that is the change in v over change in time. That means if this thing were going at a non-constant or non-uniform circular motion, that means it's not going to be going at a constant speed anymore, right? So non-uniform circular motion means speeding up or slowing down. Okay? If it's speeding up, you would have positive acceleration. If it's slowing down, negative acceleration. Okay? Just like we did in chapter 2. Okay? And that, of course, is Vf minus Vi over change in time. And because this speed at this circular path, right, happens at different times, you have to know where the initial is and you have to know where the final is. Okay? So it's very important to make sure you identify your initial position and your final position and find the time for those to figure out the initial velocity or initial speed and the final speed as it goes around the circular path. Okay? Well, then we have two different accelerations. We have linear acceleration, otherwise known as atangential, and we have radial acceleration or centripetal acceleration. Maybe I should use different color. Centripetal acceleration. And we have A sub c, right, which is v squared over r. And the direction of that is towards the center, no matter where it is in this circular path, right? So if it were at this top of the circle here, or should I say if this thing is going around on a flat table and we're looking at it from bird's eye view, right? And when it's at the top of the circle right here, it has tangential acceleration, right? Which is this, and let's say it's going faster and faster and faster. So here's the tangential acceleration, and this is the direction of motion, let's say. Right? And simultaneously, it has radial acceleration going in towards the center. Okay? So I have two accelerations perpendicular to one another. So when I add these two accelerations vectorially, right, I would have A tangential plus A radial, and this would be my A total. This is the total acceleration. Okay? So my A total is vector addition of A tangential and A radial. Okay? Now let's take a look at it when, let's say what happens if this thing were right here. In this case, if we were speeding up, my A tangential would get bigger if we were speeding up. So now it's like this big instead of this big, right? My radial direction, because it's speeding up, most likely it's going to be even bigger than that, right? So here's my A radial. And here's my A tangential. This time, my total acceleration will be A tangential plus A radial, and it will be that as my A total. Okay? Again, similarly, if this thing were going in a counterclockwise direction, if it were here, let's say now, right? Now it's going to be even going faster, but I cannot draw this really big, right? I mean, my A tangential will be like going up this way, maybe this big, right? Because it's speeding up now, right? I'm sorry. Now that would be a jerk, actually. Let's say A tangential is constant. Let's make it easier. Okay. Let's say A tangential is constant instead of jerky motion where this is actually changing acceleration. Let's say it is staying constantly. Constant acceleration. Let's make that easier. In that case, if this were here, it would be the same magnitude as that. That means my acceleration is constant now, okay? Okay? But speed would be changing. Okay, speed would be changing. Then my A radial will be going in this direction. Okay, so A radial will be going in this direction, and my A tangential will be going in that direction, and this would be my A total. Never mind this long, I drew it long here. Draw the same length as this. Let's make it easy instead of trying to make it more difficult. This will be a very jerky motion because derivative of acceleration is jerk. And I don't want it. Let's make it constant acceleration. Okay, so let's do that instead. That means this is where it's like that. Let's do it this way because I don't want to make it even more complicated than it is. All right, so let's keep these magnitudes the same and let's make A tangential, A radial, A tangential, A radial, and this is the A total and this is A total. Okay? So how do we find the magnitude of my A total? Well, since they are perpendicular to one another, right, you can actually make a right triangle, right? Whether it's here or here, right? It'll make a similar right triangle where if I were to look at it here, right, here is my A radial, and here is my A tangential, right? And here is my A total, right? Similarly, if I were to look at it here, it would be my A radial, A tangential, and here's my A total. It would still be a right triangle with the same sides of magnitude on each, right? So here, this is 90 degrees. So the magnitude of that A total, right, will be just square root of, right, A tangential squared plus A radial squared, which is same as AC, right? So if you want my A total, the magnitude of the A total is equal to square root of, well, A tangential, we know what that is. That is delta V over delta T. And we have to square that. Plus A radial, we know what that is. A radial is V squared over R quantity squared. So find these separately and then use Pythagorean theorem to figure out the A total. Okay? So here we go. Let's take a look at this. Here, a race car starts from rest. That's our initial velocity in the pit area and accelerates at a uniform rate to a speed of 30 meters per second. This uniform rate means constant acceleration, okay? Constant acceleration. That means it's speeding up consistently from 0 to 30 meters per second. So this is my V final. In 11 seconds, that's my time t. Okay? Moving on a circular track of radius of 500 meters. Okay? So let's write down everything we know. So we know initial velocity, right, is 0. Right? We know the final velocity or final speed is 30 meters per second. We know the time is equal to 11 seconds, and R happens to be 500 meters. Okay? Determine the tangential and centripetal components of the total acceleration. They want us to find out what the total acceleration is, right? At 11 seconds. Okay? At 11 seconds. Okay? So, if this thing started at rest and then start to accelerate and then goes faster and faster and faster to 30 meters per second, we don't know where it is, and we could probably figure it out, right? We want to know at that point. So let's have a little visual here. Let's say here's the pit, and then the car starts at 0 here, right? So VI is equal to 0, and then it goes faster and faster and faster and faster. Let's say right around here, VF is equal to 30 meters per second. I'm just, I'm not exactly sure if it's going to be here or not. It could be here, it could be here, but we could figure that out, right? We can definitely figure that out. But here, this is R, right? Here, this is R, and R is equal to 500 meters. So at this point, we have two accelerations. One being A radial, right? So this is A radial or A centripetal, and this will also have A tangential. And we can figure out the A total, the magnitude. Okay? So if I were to redraw this, right? So here is my A radial, right? And here is my A tangential. Right? And this is my A total. But this here is 90 degrees. Right? So this is A total. So since they want us to figure out, right, tangential and centripetal components, well, we could figure out A tangential pretty easily. And that is equal to delta V over delta T. And that is VF minus VI over delta T. So VF, 30 meters per second, minus 0 over 11 seconds. Right? So if you work that out, you're going to get 2.73, right, meters per second squared. Now here, ready? This is the tan hat, tangential hat, the unit vector in tangential way. Okay? For A radial, at this point, it is V squared over R. But this V is at V final, right? Because it's at this point, which means it's moving at 30 meters per second. And that is equal to, right, 30 squared over R, which is 500. And that comes out to 1.8 meters per second squared. Radial hat. R hat, right? Radial hat. So if we were to represent my A total in vectorial form in Cartesian way, right, it would be 2.73 tan hat, right, plus 1.8 radial hat, right, meters per second squared. Okay? Now let's take one step further. What is the magnitude of this A total? What is the magnitude of that? Well, that is simply nothing more than just square root of, right? 2.73 squared plus 1.8 right, squared. And if you do that, I think it comes out to square root of like 10.693. So A total comes out to 3.27 meters per second squared as the total acceleration's magnitude. Okay? All right. And last page. Well, actually not the last page. Here, we have an example problem of non-uniform circular motion. A particle moves clockwise. So when it's moving clockwise, what does that mean? It means it's going this way, right? This is analog clock, not digital clock, right? That's what clockwise is. Counterclockwise is the opposite direction. With a circle of radius of 1 meter, so radius has only 1 meter, it starts at rest at the origin at time t is equal to 0. So I'm assuming A is the origin, right? Right here. Right? Here, t is equal to 0. Its speed increases at a constant rate of 1.6 meters per second squared. That is my A tangential because it's going faster and faster and faster. It's like first second it's moving at 1.6 meters per second. Second, like 3.2 meters per second, and so on. It's going to go faster and faster at this rate. Okay? How long does it take to travel halfway around the circle from point A to B? Assuming, right, it starts at rest. So here, my initial velocity or initial speed is 0. So here, V initial is equal to 0. Okay? So, when it travels in this circular arc right here. Okay? This circular arc is distance s. So here, s is equal to distance traveled, right? That s is equal to half a circle, right? So 2 pi r over 2, or just pi r. Okay? Well, it travels this much distance starting at 0, finishing it up, we don't know. Right? They want to know how much time, right? How long, I guess they want to find time. So they want to know time. We know initial velocity or initial speed is 0, right? And so they want how much time at point B, right? And they also gave us acceleration, which is 1.6 meters per second squared. This looks familiar, right? We could probably use one of the equations, right, from constant acceleration equations, right? So let's do that. Which equation should we use? I would say equation number 2, right? The distance is equal to VIT plus 1/2 AT squared. We know the distance is pi r. And pi r is 1, so pi times 1. That is equal to initial velocity or initial speed is 0, right? Plus 1/2 times 1.6 times t squared. So 3.1415 is equal to, right, 0 plus, right, 0.8 t squared. So my t is equal to square root of this divided by that, right? So if you do it correctly, you should get 1.98 seconds. Now, of course, there are other ways to do this, but this is probably the most efficient way. All right. So let's take a look at the next. What is speed at point B? Well, we know time, right? We know time. We just calculated that to be 1.98 seconds. We know the initial speed is 0. We know acceleration is equal to 1.6 meters per second squared. We're looking for speed v final at point B. Therefore, we can use equation number 1, which is Vf is equal to Vi plus At. Vf is what we're looking for. Vi 0 plus 1.6 times 1.98 seconds. So when we solve for Vf, my Vf is equal to, I get something like 3.17 meters per second. All right. Then C asks, what is the direction of its velocity at that time? So we're looking at point B, right? So if this thing were moving in a circular path at point B, the velocity, which is tangential velocity, is going to be pointing downwards because it has to be tangent to the circle. So it has to be pointing down like this. So this is my V at point B, right? So the direction will be down, or negative y hat. Here is asking, what is the centripetal acceleration or the radial acceleration? So if you were to look at the radial acceleration at this point B, right? So here again, right? Well, radial acceleration is in this way towards the center, so A sub C, right? And A sub C is equal to V squared at point B, right? V at point B squared over R. And that is 3.17 squared over R, which is 1. And I get 10.05 meters per second squared. Now, since it's going in this direction, I would say negative x hat, okay? So if you want to, you can say negative x hat. Or you could simply say towards the center of the circle, okay? So if you want to make it more consistent, that will be the proper notation for A sub c. E, what is the tangential acceleration? Well, we already know that, right? Here's the circle, here's B. Tangential acceleration is going to be tangentially going down this way, tangentially, and that's A tangential. And we already know that A tangential is going to be 1.6 all the time, because this will be a constant acceleration. It won't be a jerky motion, right? And again, it will be negative y hat. Okay? So if you want, you can say A tangential is equal to, right, 1.6 meters per second squared y hat. Okay? You could do it that way. And this will be the A sub c, A radial. All right. Then, F. What is the magnitude and direction of the total acceleration at point B? So at total acceleration at point B, right? So here we have A tangential going down. So 1 point, right? So A tangential. And then we have A radial. Right? So if we were to add these vectorially, right, what do we get? We get, so it doesn't matter which one I add first. So here I get my A radial plus A tangential. Right? And here's my A total. Right? This angle right here is my reference angle beta. Okay? We already know what A radial is, and that is 10.05. And A tangential is 1.6. Now, yes, you can put negative and negative. You can do that, definitely. But for now, since I'm looking for just the magnitude, I could just use these values without the negative because they're going to be squared, right? So let's find the magnitude. So A total, right? The magnitude of A total is equal to square root of is simply 1.6 squared plus 10.05 squared. Okay? And if you work that out with your calculator, I think you'll get something like 10.18 meters per second squared as the magnitude of my total acceleration. However, if I'm looking for this beta, this reference angle beta is equal to, right, tan inverse of, right, opposite, which is negative 1.6, right, because it's in third quadrant. But it's going to get canceled out anyway, right? And negative 10.05. So my angle beta, which is the reference angle right here, right, is going to come out to, I believe, 9 degrees. So since it's 9 degrees here, and if you were to look at, you know, the XY coordinate system right here, this would be the proper angle from here all the way down here. So that would be my theta. So my theta is equal to 180 plus my angle beta. Therefore, theta is equal to 180 plus 9. So 189 degrees is my angle. Okay? So if you were to write my A total in the magnitude and direction form, it would be 10.18 meters per second squared, comma, theta is equal to 189 degrees. Boom. Okay? All right. Any questions? All right. Good. All right. So let's take a look at dynamics of circular motion. Okay. I wish I was doing this in person because it would really make more sense if I would show you with my tennis ball and a string attached to it, and if I show you in person, it'd be so much better. However, let's see if we can imagine this. Okay. Remember Newton's second law, right? Newton's second law is stated: sum of all forces, or the net force, is equal to ma. However, when things are going in a circular motion, that same sum of all net forces, instead of setting it equal to ma, we set it equal to mac. Mind blown. So hard. Now, remember we set this equal to all the forces acting, right? So ma is equal to whatever force plus whatever force plus whatever force. Same thing. mac now is equal to whatever force plus whatever force plus whatever force, and then set them equal to each other. It's that simple. Okay? So instead of using a sub x and a sub y for ma, we'll just use mac, or mv squared over r is my new Newton's second law. Okay? So the net force now is equal to mac. Okay? You do not draw this in a force diagram. This is what you set it equal to, right? The force diagram, you just draw whatever is causing that force. For this instance, when things are going in a circular motion like this, the string is what's making this thing go in a circular motion. And the string, you have to pull it in towards you in order to make it go in a circle. Because imagine this circular thing as your dog. Assume a spherical dog, right? And you're taking a dog out for a walk, right? And your dog is very well disciplined, so it's walking parallel next to you with a leash, and you're walking. And then let's say you stop, but your dog wants to keep going straight. But as long as you're holding onto the leash, right, you pull the leash towards you, and the dog's going to go, oh, I want to go straight, but no, you're not. No, you're not. No, you're not, right? No, you're not. So the tension will always be pulling towards you, and dog will actually go around you in a circular motion. Matter of fact, that's sort of same thing what's happening with the moon, right? The moon wants to go straight, but the Earth is saying, no, you're not. No, you're not, right? Because there's gravitational pull between the moon and the Earth. So there's invisible force that's pulling towards the Earth, saying the moon cannot go away. It's going to be going around the circle like the dog on a leash is going around the circle. I mean, it's not exactly the right terminology, but I think there's a good visualization, right? So the center seeking force has to be what's causing that object to go around in a circle. And that center-seeking force is the tension towards the center of the circle. Okay? It doesn't always have to be just one force. There could be multiple forces that's making it go in the circular motion, or it could hinder from going in the circular motion. You have to visualize this motion where the observer is out of the system. Don't place yourself as the ball or the dog, right? Place yourself away from the system, observing it as a third party. Okay? If you are the dog, things are different because now you are in a non-inertial frame of reference because you are being accelerated, right? If you are the one being, rotated around, then you would actually feel centrifugal force that's actually center fleeing force, okay? So that's a different thing when you place yourself in a circular motion. All these problems are happening where you, the observer, is away from the system, observing this in a third party, right? So please keep that in mind. That's very, very important. Now, the centripetal or center seeking force causes circular motion, not centrifugal. Okay? This is center fleeing. This only happens if the observer is being spun around, okay, in a non-inertial frame of reference. So the force that is acting on the ball, causing the circular motion, is inward, okay? So the tension actually has to be pulled in towards the center of the circle for this ball to go around in a circle. The force acting on the hand is outward and not causing the circular motion. The centrifugal force is a fictitious or pseudo force caused by viewing the situation from accelerating frame of reference. So this is when you place yourself in the circular frame of accelerated frame of reference. But you don't want to do that. That complicates things. All right? So there used to be this like really cool ride in Wildwood, right? They call it a Rotor Ride. It's a circular room, right? You go in there and it's dark and it's smelly, and then you stay against the wall, right? I think it was called Hellhole back in those days when I was really young, and that was like really far back, young, like with dinosaurs. Well, anyway, this circular room would actually start to spin, right? When it starts to spin, right, people actually get stuck to the wall. Okay, people get stuck to the wall. Now, don't place yourself in there yet. Don't place yourself inside this ride. Okay, so as this hellhole ride actually goes in a circle, right? The riders get stuck against the wall, right? And the floor starts to drop. When the floor drops, there are paintings on the wall and below the floor with fire and devil with pitchfork, and then like the riders are stuck against the wall and they're all screaming, and of course some of your friends are trying to like stand up or trying to go upside down, trying to show off from the girls, right? But generally they're stuck against the wall. And as long as this ride is spinning fast enough, you're not going to go to hell. All right? Well, let's think about all the forces that's keeping you from going to hell, right? What's keeping this rider from going to hell is friction. Because the obvious force is going to be Fg. Fg is going to be the obvious force, the weight. And the weight's going to pull you towards hell. But what's keeping you, or I'm sorry, not you, the rider from going to hell is the friction that's countering the weight of the rider. Well, what's keeping this rider in a circular motion? If this ride just suddenly disappears. These walls just go gone. The rider would fly out tangentially towards, I guess, the water, right? Atlantic Ocean, or towards, like if it's here, towards the boardwalk, right? So, or other rides. They just fly off tangentially. But the wall is saying, no, you're not. You're not flying off. You're not flying off. You're not flying off. And the wall is pushing the rider towards the center, right? So the rider stays in that circular path. So the wall pushing on the rider is my F normal. This F normal from the wall towards the center of the circle, right, is keeping this rider in this circular path. Okay? Well, if we break this up into two components, don't worry about this yet, right? We'll talk about this when I put you in the ride and you are observing yourself in that ride. But don't worry about this yet, all right? If I look at sum of all forces, right, in the x direction, right, sum of all forces in the x direction, I have MAC, because centripetal force is what's causing this going in a circular motion. And in the x direction, there's only one force in the x direction, and that's towards the center of the circle, and that's my F normal. We're going to make A sub C as positive direction all the time. Okay? So as long as the force is in towards the center, we call it positive. If force is out of the center, then we call it negative. So we set these two equal to each other and say MAC is equal to my F normal. Because F normal is pointing towards the center, it's staying positive. So what's my F normal? My F normal is equal to then M times V squared over R. This R is the radius of the ride. This V is how fast this thing is spinning. Okay? Let's take a look at the Y direction. Sum of all forces in the Y direction is equal to MAY, right? Well, you don't want acceleration in down direction or else you'd be going to hell, right? And friction is a reactive force. It'll never pull you up. It'll just hold you there, but it'll never pull you up. So the acceleration in Y better be 0. Well, how many forces are there in the Y direction? Well, there are Fg, right? There's Fg, and there's friction. We're going to call, right, one of them positive and the other one negative. Okay? Let's call Fg positive. So here, when we set these equal to each other, 0 is equal to, right? 0 is equal to Fg, wrong color, sorry, Fg minus friction. So friction, if I bring this to the other side, it becomes positive, is equal to Fg, or simply mg. So what is friction? Friction is equal to mu times F normal. And that is equal to mg. This mass is the mass of the rider. But we already found out what F normal is. F normal is mv squared over r. So mu times, right, mv squared over r is equal to mg. And here's the magic. Look, the masses cancel out. So everyone inside this ride gets stuck to the wall as long as they have the same coefficient of friction. That's why the riders tell you, or the ride operator, you know, the guy with like missing teeth and it's like smoking a cigarette saying, sit down, kid, you know, you're gonna get hurt, you know. Well, he always makes you wear a shirt when you go inside the ride. Because if you don't have a shirt on, because of the suntan lotion and coconut oil, your mu drops to very low value. And when that happens, you're gonna go slide down to hell, right? But if you have a shirt on, because of the shirt and the wall, it's gonna keep you, right, from going to hell. Okay? So if you want to figure out what the minimum mu is, all you have to do is calculate for it. Because you know the radius of the room has to be constant. And when they reach the certain speed that ride can achieve at the maximum speed that ride achieve, that's going to stay constant. Right? So if you want to figure out the minimum coefficient of friction, right, you could calculate that as Rg, right, as Rg over v squared. So that will prevent you going from hell. I will end my lecture there. All right. Take care, everybody. Yeah. I'll see you next week from school. All right. Have a nice day.